Hello, it's Stat 135, Lecture 29. Last time we covered sections 11.2 and 11.3 on non-parametric tests for comparing the distribution of two continuous populations. Today we're generalizing that by considering a parametric test comparing the means of greater than or equal to two continuous populations. So this is using normal theory and in particular the F-test, which is a generalization of the t-test. So the analysis of variance, known as ANOVA, we're going to be concentrating on a one-way layout, which is an experimental design in which independent measurements are made under each of several treatments. So in this picture here, we have 7 treatment groups and 10 observations per treatment group. This is represented in this box plot below. So if you just imagine that the bar in each box is the mean instead of the median, and I've drawn out the mean for the total sum of our data from the 7 labs, then essentially what we're showing, what we're claiming is that the mean for all of these labs are the same. And so let's see what we have here. So our question is, are the means of each treatment group the same, or is at least one of the means different? And if there are only 2 groups, then you can answer this with a t-test, of course. So I'm just going to do the transpose of sort of our picture here. So I'm going to put the treatment groups for my rows, and the observations are going to be columns here, just to be consistent with what we had in chapter 11. So Yij is the jth observation of the ith treatment group. In the margins here, I have the averages for each of the I treatment groups, and at the bottom here, I have the average of the averages of the row averages, y bar dot dot. So my model is going to consist of the overall mean mu plus some differential effects of the ith treatment plus some noise. So I think of mu and alpha I as constants. The alpha i's are normalized in the sense that they sum to 0. And hence the yi's, so the noise is normal 0 sigma squared. So the yij's are normal mu plus alpha I with variance sigma squared. And as I said, my null is that the alpha i's are all the same in 0. And the alternative is that not all the alpha i's are 0. And ANOVA is based on this very important identity that we'll see several times in this course, in particular ANOVA and regression. So the sum of squared totals. So the sum of squared totals is the sum of squares within plus the sum of squares between. So the sum of squares total is you're summing over i's and j's, and you're looking at the difference of the yij's from the total mean, that difference squared. The sum of squares between, the sum of squares within is sort of the intra-group differences. So you're taking yij minus the row means squared, and the between, the sum of squares between, you're taking the differences between the row averages and the total average. So the row averages and the average of the row averages. So this says that the spread of your data about the mean has 2 sources: the spread of data about their group mean and the spread of the group means about the total mean. And the book on page 480 gives a proof which is algebraic, not super insightful. I think I would rather just work through a toy case to show you how it all works. I do want to mention that SSW and SSB are independent random variables. This follows from chapter 6. In chapter 6, we mentioned that the sample mean and xi minus the sample mean are independent random variables. And so here SSB is a function of the row means, and that's because so SSB is the differences of row means and the total mean, but the total mean is actually the average of the row mean, so it's all a function of row means. The SSW is a function of the Yij's minus the row means. So there you go. That shows that SSB and SSW are independent. So here's an example. So imagine that I have 3 treatment groups and 3 observations in each treatment group, with data shown here in this 3x3, and I've written out the averages for the rows and the total average. I just want to recall from chapter 6 that n-1 times the sample variance over sigma squared is a chi-squared with n-1 degrees of freedom. And the SST in this case is the sum over all i's and j's of Yij minus the total mean squared. And so you get 9 terms, and the sum of the SST is 30. Now, the SST divided by ij minus 1, which is the total number of terms minus 1, that is the sample variance. And so ij minus 1 sample variance over sigma squared is which is the same thing as SST over sigma squared. That's a chi-squared with ij minus 1 degrees of freedom. So we say that SST has ij minus 1 degrees of freedom. Even though SST isn't a chi-squared, SST divided by sigma squared is a chi-squared with ij minus 1 degrees of freedom. So our sum of squares within. So here, so I find the group sample variances. So I denote that as S squared A, S squared B, S squared C. And so J minus 1 times that is just the sort of the sum of squares along each of the rows. And so the sum of squares within is just the sum of these of J minus 1 sample variance for A, plus J minus 1 sample variance for B, plus J minus 1 sample variance for C. And so this is really, so you can form the pooled variance, which is really just the average of, it's just the average of these, of the row sample variances, right? The J minus 1s cancel here, so you just get S squared A plus S squared B plus S squared C divided by 3. It's just the average of so the pooled variance is just the average of the group sample variances, and that's SSW over I times J minus 1. So I times J minus 1 pooled variance over sigma squared is a chi-squared with I J minus 1 degrees of freedom. So we say that SSW has I times J minus 1 degrees of freedom. Finally, we get to SSB. And SSB, so that's the differences of the row averages from the total average squared, and so we can write down the sample variance of the of the row averages. So I write that as S squared y bar I dot. And so the SSB is j times I minus 1, the sample row variance, how do you say that? So it's the sample variance of the row means. There you go. And so notice that the row means is the average over j. So it's the average of the yij's over the total number of observations that we have, which is j. And so the variance of this, you can approximate it two ways. So you can approximate it as, well, it's the sample variance of the row means, or writing the variance as 1 over j sigma squared. You can approximate sigma squared by the total sample variance. So 1 over j sigma squared is approximately s squared over j. So we get this equality here. It's actually an approximation that the sample variance of the rows of the row means is s squared over j. And so this allows us to write the SSB as j times I minus 1 times the sample variance over j. The j's cancel, and hence we get I minus 1 s squared over sigma squared is a chi squared with I minus 1 degrees of freedom, and hence we say that SSB has I minus 1 degrees of freedom. So now we can see from numerically that SST is SSW plus SSB, but more, because 30 is 6 plus 24, but more is true. The SSB and SSW are independent, and so since SSB over sigma squared and SSW over sigma squared are independent chi-squareds, their degrees of freedom should add up. And in fact, you can check that they do. So I times j minus 1 plus I minus 1 is, in fact, ij minus 1. In other words, 3 times 2, which is, so 6 plus 2 is 8. Yes, we can count. So there you go. I hope you enjoy that, and I'll see you next time for more ANOVA.